deploying massive vision models on edge devices usually means relying on knowledge distillation. But when you try to distill from a transformer into a CNN, the training process frequently collapses. Why? Because you're forcing two fundamentally different architectural priors to optimize the same space. Today, we're breaking down SPOFA, a new framework that solves heterogeneous knowledge distillation by explicitly decoupling feature geometry and regulating gradient conflicts with near-zero overhead. Heterogeneous knowledge distillation aims to transfer knowledge across architectures with different inductive biases. A vision transformer relies on global self-attention, while a CNN depends on local receptive fields. When you try to align them, two highly coupled problems emerge. First, at the feature level, you get massive norm discrepancies. Transformers naturally generate unbounded, large-magnitude feature vectors. CNNs expect normalized, localized variance. If you force the student to mimic absolute feature magnitudes, it hits a representational bottleneck. The network wastes its limited capacity fitting arbitrary scalar norms instead of aligning semantic directions. Second, at the gradient level, you get severe optimization conflicts. The distillation gradient and the primary task gradient frequently point in opposing directions because the architectures dictate fundamentally different descent paths. Existing methods use static or memoryless dynamic weights, which just amplifies the noise and causes catastrophic forgetting of the primary task. SPOFA tackles this with a dual stabilization paradigm. At the feature level, it introduces a minimalist LayerNorm-based decoupling projector. Instead of using a standard linear projection that entangles magnitude and direction, SPOFA inserts layer normalization directly into the auxiliary distillation branch before the final classification projection. This normalizes activations across the channel dimension for each spatial token independently. The result is that feature magnitude is explicitly decoupled from directional alignment. Since the teacher is frozen with constant feature magnitudes, the student only needs to align its relative logit distribution. When paired with temperature-scaled softmax, which inherently relies on relative probabilities rather than absolute logit magnitudes, this single-sided structural decoupling cuts off the gradient pathways responsible for arbitrary magnitude scaling. The optimizer is forced to focus entirely on maximizing angular consistency between student and teacher representations. But feature alignment alone isn't enough. Knowledge distillation is fundamentally a multi-objective optimization problem. Even with perfectly aligned features, the gradients from the ground truth loss and the distillation loss will still clash. SPOFA addresses this with a momentum-driven exponential moving average, or MEMA, dynamic scalar. Instead of relying on volatile, instantaneous gradient metrics, MEMA establishes a robust historical baseline of the optimization trajectory. It probes gradient conflicts at the output logit level, which is computationally crucial. Calculating per sample gradient similarities across the entire parameter space would cost O(ND) per step, where D is the number of parameters. By evaluating gradients strictly at the logit bottleneck, SPOFA reduces this to O(NC), where C is the number of classes. This is orders of magnitude cheaper and seamlessly fits into standard training pipelines. MEMA computes the instantaneous cosine similarity between the primary and distillation gradients for each sample. It then maintains an EMA baseline of this similarity. The framework uses a strict penalty-only mechanism. It calculates the deviation between the current similarity and the historical baseline. Only when the instantaneous conflict drops significantly below the historical expectation does it trigger a weight decay. This is backed by a theoretical guarantee. If the gradient similarity is negative, the distillation weight must stay below a strict upper bound to ensure the joint update remains a descent direction for the primary task. MEMA acts as a structural safeguard that dynamically throttles the distillation influence inversely proportional to conflict severity, keeping the optimization trajectory stable. The results speak for themselves. On CIFAR 100 and ImageNet 1K, SPOFA consistently outperforms the strong OFA baseline and recent state-of-the-art methods like PAT across diverse heterogeneous pairs, including transformer to CNN, CNN to transformer, and MLP to CNN transfers. In many settings, it achieves state-of-the-art accuracy while introducing virtually zero extra trainable parameters during training. Unlike PAT, which relies on heavy auxiliary attention modules and dual teacher forwarding, SPOFA's parameter footprint is practically identical to lightweight baselines. And because all auxiliary modules are discarded after training, there is strictly zero extra inference cost. The student model deploys exactly as it would without distillation, but with significantly higher accuracy. Heterogeneous knowledge distillation has long been bottlenecked by representational inertia and gradient chaos. SPOFA shows that you don't need massive attention modules or heuristic weighting to fix it. By explicitly decoupling feature geometry and regulating gradient conflicts through a momentum-aware baseline, you can achieve stable, efficient, and high-performance knowledge transfer. As the field pushes toward more diverse model architectures and multimodal alignment, these principles of structural decoupling and trajectory-aware optimization will only become more critical. If you want to dive into the full mathematical derivations, ablation studies, and training pipeline details, the paper is linked in the description. Thanks for watching, and I'll see you in the next one.